Hello, can you hear me?
Yes.
How are you guys doing? Um, okay, let me start by showing you the classroom. Let's try and open it up right here. It's a classroom. Okay. Yeah, I think you can see the classroom now. So this week, we start the probability theory. And then if you can see from my announcement, what is due this week, week 10, we have um, classwork 7, which I will put there after as soon as we finish, and homework 5, which is due on April. Classwork 7 is due tonight. However, if you submit it tomorrow, I will still accept it. So you can access them by going to the models, scroll down to module 4. This is where you can see the document we are using for today. Classwork 7, I'll put it as soon as we finish. I mean the question. And homework 5 you do on the Access Pearson. You already know that. Now, in April, second week of April, if you are failing the class or if you're not doing well in the class, in second week of April, if your attendance is up to 70%, you can request for a makeup. And I'll give you makeup for up to 3 assignments or 4, depending on the situation. But your attendance has to be 70% or more before you can qualify for the makeup. Any question before we begin? Okay.
No.
All right. So let's start then. So today, like I said, we had a new chapter, a new topic, probability. I'm sure you must have heard of this before. The probability of an event means the likelihood of that event occurring. That's the simplest way to explain it. The likelihood of that event occurring. So an event that is you are sure that will occur have a probability of 1, which means 100%. If it cannot occur, it has the probability of 0. So example, I'll give some example here. You can, when you download the document from the model, you can see all this. I say an event with a probability of 1 can be considered a certainty. For example, when tossing a coin, even that it will result to head or tail is 1. But for impossible event, the probability is 0. Now, how do we write probability? You can write them as a fraction or as a ratio. Fraction is like 7 over 10 is a probability. Or 7 to 10. That's another way you can write probability. Or as a percent. 70%, for example, is also another way you can write it. Decimal, like 0.7. So I'm just using 7 as an example. There's other numbers you can get from the probability. Which bring us to the concept of probability experiments. So what is a probability experiment? In plain terms, a probability experiment simply means those chance processes that lead to well-defined results that we call outcomes. For example, when you flip a coin, the probability can be either it land on head or tail. So that is a good example of a probability experiment. The same thing with dice. I'm sure that by now you must notice that these 3 examples I gave here have to do with lottery, because the probability concept actually was, I would say the concept was initiated by gamblers. But after a while, it was realized that it can be applied to other aspects of life, like in education, science, technology, and so on and so forth. Even genetics, human genetics. So many examples we'll be doing will be involve gambling. They actually initiated it, and they won a lot of money with that. Now, buying a lottery ticket is also a good example of a probability experiment because it have outcomes, well-defined outcome. Either you win or you lose. So when we keep saying outcome, what is an outcome? An outcome simply means the result of a single trial of a probability experiment. For example, when you toss the coin, the outcome is head or tail. So when you buy a lottery ticket, the outcome, okay, for a coin, say head show up, we normally put them inside brace brackets. Outcome should be head or tail. Okay? When you buy a lottery ticket, the outcome is either you win or you lose. Okay? Yep. Now, when you take an exam, either you pass or you don't pass. So you can see the coin and the dice. Now, sample space, very important when when we are discussing probability, because sample space will be the denominator you have when you do your calculations. A sample space is a set of all the possible outcomes of a probability experiment. So that, from the example I just gave you, when you roll a dice, a dice have 6 sides, a 6-sided dice. So the outcome can be, the sample space would be 1, 2, 3, 4, 5, and 6. Whenever you roll the dice, any of this number will show up. Any of them can show up. So it's sample space. Day of the week, we have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So this is a sample space for any day of the week you pick must fall within any of these days. So all the possible outcomes, the set of all the possible outcomes of a probability experiment. Now we can use tree diagram to get sample space. Especially if it is something that we don't know exactly, like the day of the week, we know that based on our calendar, we kind of calendar we use, I think it's called Gregorian calendar or something like that. It's 7 days in a week. Where I come from, as a matter of fact, I'm from the Igbo tribe in Nigeria. Our own days of the week is 4 days, and they are named according to the market days. But Nigeria now use the regular days of the week, Monday to Sunday, because now we were colonized by the British, so we are using British style modern education. Anyway, I think you get the point. So we can use tree diagram to we can use it to get the sample space when especially if we don't know the exact the constitution. Let me put it this way. If we have to, unlike the days of the week where we already know that it's 7 days, there are some events that we don't know the sample space. We have to actually estimate it. In that case, the tree diagram will help us to do it. Now, look at this example. It says, find the sample space for the gender of 3 children of a couple. Use a tree diagram. So in that case, gender is boy, B, and girl. So the first child should be, let's say the first child should be, okay, I'll start from here. I'm gonna use, let me use this. The first child, okay, should be boy or girl. And that is what is well, even if there's some situation whereby um due to kind of birth defect, a child may carry the same both the female and male organ in its body. But in that, even if it happens, only one of them will be functional. The other one will not be functional. And the one that is functional is the one that will be the gender of the baby. Now, for second child, now you break these two A, B, and G into two components, each of them boy and girl, so that we have okay, boy, yeah, boy. I'm gonna put the letters in a minute. It's going to be boy, girl, and this is boy and girl. Now the third child, you break this up into each of them into two components. Okay, so we have it in this form. For this one, we have two components for boy and girl. Okay. Okay, and this one, boy, girl, boy, girl. So this one is boy, and this one is girl, boy, girl, girl. This one is boy. Okay, let me make it this one. Okay, let me boy, and this one I'm gonna adjust this a little bit. Okay, girl, and this one is boy, boy, and this one is girl. So now with this is what they call it. It looks like a tree. That's why we call it a tree diagram. Now let us get the outcomes. It can be that the first child is a boy. Okay. First child is a boy, second child is a boy, third child is a boy. So the outcome here will be boy, boy, boy. It can be that the first child is a boy, second child is a boy, third child is a girl. Boy, boy, girl. It can be that the first child is a boy, second child is a girl, third child is a boy. Boy, girl, boy. It can be first child is a boy, second child is a girl, third child is a girl. So boy, girl. So you can see how it goes, which means that this one will be girl, boy, and boy. Girl, boy, and boy. This one will be girl, boy, girl. Girl, boy, girl. And this will be girl, girl, boy. Girl, girl, boy. And this will be all girls. Okay? All girls. So you can see the sample space. How many possibilities? Okay. Let me undo this. So the sample space will be all the possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8 possibilities. Any family that have 3 kids, then if you check this gender, it must fall within any of these categories. Does anybody have a question for this? Okay, no question. Good. Excellent. Now, let us see if we can answer some question with this. It says, find the probability that the family has 2 girls and a boy. Now, for 2 girls and a boy, look at the what they give us 2 girls and a boy. This is 2 girls and a boy, GGB, GBG, 2 girls and a boy, BGG, 3 of them. So 2 girls and a boy will be, the outcome will be, we have 2 girls and a boy, BGG, comma, and I can give us 2 girls and a boy, GBG, GBG, comma, and then we got GGB. So that the probability of 2 girls and a boy will be 3 of them. 3 out of 8 possibilities. Okay? 3 over 8. You can get it from the calculator. What it means? 3 out of 8 possibility. Let me see, bring the calculator. 3 over 8. Okay. You got 3 divided by 8. 0.375. 2.375. Okay, 0.375. Or if you like, you can call it 37.5%. Okay. Now you can even be asked the probability that there are all 3 gears. For 3 gears, have only one outcome. GGG.
Excuse me.
Yes, sir. Go ahead.
Do we copy this now?
If you like, you can copy it, but remember you have I have this recorded anyway, so you can watch it.
Okay. So we don't have to like.
If you go to YouTube, type my name and type probability, you get different videos I make on it, including this one. You can watch it.
Okay.
Mhm.
All right. Thank you.
You're welcome. So that the probability of that for 3 gears is 3G. You can take 3Gs, 3 gears. For 3 gears, you have 3Gs. And that's only one outcome. So that the probability of 3 gears will be 1 outcome out of 8 possibilities. Okay? 1 out of 8 possibilities, which you can have here, changing this to 1, give you 0.125. 0.125. 2.125. Or I can call it 12.5% chance. Okay? Now, any question on this? Okay. Now, since there's no question, I will continue. And one concept we need to learn is a concept that is called events. Now, an event simply means a set of outcomes of a probability experiment. And we have 2 types. We have simple event and compound event. Simple event have only one outcome. For example, when you roll a dice, getting a 6. Okay? So outcome is just 6. See, it's only one outcome. Roll a die, getting a 6, a 2. Outcome is 2. That's only one outcome. Getting 1 day in the days of the week. Let's say that you want to make an appointment with your doctor, and then they give you an appointment on Monday. That is only one event. So it's only one event, one outcome, Monday. Okay. Now that is for simple events. Now compound events have 2 or more outcomes. For example, the event of getting an odd number when a dice is rolled. They say that a dice is rolled and getting an odd number. Well, odd number, a dice has 1 to 6 There's different sides of the dice. There's a side that has 1 showing up, and there's a side that have 2 showing up, and so on. So even numbers will be getting an odd number. Let me call it here. This is odd number. Okay, odds number will be for a dice of 6 sides. 1, 3, and 5. That's the odd number in the dice. So you have more than one outcome. More than you have 2 or more outcomes. Getting a weekend, okay, will be Saturday, Sunday. So you have 2 or more outcomes. We call it compound events. Okay. So so what we do in probability, we give you an event and they ask you to calculate the probability of the event. There are other things we need to know about probability. There's one we call I think I mentioned it briefly at the beginning. The probability of an impossible event is 0. Now, if the event is unlikely to happen, then the probability will be less than 0.5, which is less than 50%. Like I said, the probability of getting COVID-19, there's a time it was very popular. It was very almost everybody had to wear a mask because they are concerned that people can just catch it very fast. But now I think we are no longer in an epidemic, so the chance of getting it is low. You can say the probability is less than 50% or less than 0.5. Or how about this? A high school student who never attended physics class but wins an international physics award at the Olympiad. I mean, I know that we have geniuses, but this one, this situation is very rare. I mean, it's less than 50%, less than 0.5. Now, for event that is likely to happen, then the probability of that event will be greater than 50. Like this one. For example, getting a H or a head when a coin is tossed is 50-50 or more. Okay? Now, we can now examine the 3 approaches to probability. First one is the classical approach, which we also call it types of probability. Classical probability, empirical or relative frequency probability, then subjective probability. For the classical probability, we compute the probability of the event using sample spaces, known sample spaces, the sample space that we know. For example, the sample space for a dice is 6. The die has 6 sides. For a coin is 2, because a coin has 2 sides. And for a card has 52 cards in a deck. So that one, we know the sample space. That's why we put them under classical probability. And under classical probability, you can see the formula for finding the probability of an event here. Yeah, you can see right there on the screen. The probability of the event E becomes number of ways event E occurs divided by the total number of outcome in the sample space. Or you can just say number of ways event E occurs divided by sample space. Now, empirical probability, this one, we don't know the sample space. So we have to estimate it by ourselves. In that case, we estimate it by observing the number of occurrences for that event and then calculating the probability from a relative frequency distribution. So then next one is subjective probability. This one we don't normally use this much because it is subjective. For example, a doctor might say, based on what they diagnose, that there's a 40% chance that the patient will need surgery. And they may not be correct, accurate. It's subjective. Yeah. So we don't normally use it. We are focused only on the classical probability and the empirical probability. So let's start with classical. Look at this one. It says find the sample space for rolling of 2 dice. For 1 dice, it is 1 to 6. But when there are 2 dice, everything changes. The first die will have 1 to 6 sides. The second dice will have 1 to 6 sides. So we have to combine them. For example, dice, this is dice 1, this is dice 2. Now, the first outcome should be 1 and 1 showing up. You can see right here. Or it can be 1 and 2 showing up, which is right here. It can be 1 and 3 showing up, which is 1, 3. 1, 4, 1, 5, 1, 6. Or it can be 2 and 1 showing up. This 2 and this 1 showing up. You can see 2, 1. 2, 2 showing up, 2, 2, and so on. So that's how you got this table. So for 1 dice, it's 6 sides, 6 outcomes. But for 2 dice, it's like 36 possible outcomes, sample space for 2 dice. That is how it's prepared. So sample space will be 36. We count them. We count these numbers here, these groups. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. 36 outcomes. Outcomes. We have 2 dice. You can see how it changes. If it is 3 dice, it will even be more. It will be 6 times 6 times 6. That would be a lot. Anyway, I think you get the point. Now for the dice, for a card, it says find a sample space for drawing 1 card from an ordinary deck. You can see the deck. See the club, diamond, heart, spades. You see the aces and jack and queen. So each suit, like this club, how many cards in a club? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So they want to find a sample space. Each suit have 13 cards on it. So club is 13, diamond is 13, heart is 13, spade is 13. So I give you 13 plus 13 plus 13, give you the 2 cards. That's the sample space right there. Okay. So we can now, at this point, we're ready to try some example under classical probability. Okay. Before we do that, any question for me?
I have a question about the classwork, professor.
Yes, sir.
So I just tried opening it and it says instructions, but it has nothing else. It just says instructions.
Yes, so I'll put it after the class.
All right, thank you.
You're welcome. And the classwork will be, I want you to use handwritten, no typing. When I put it, the question, you write the question out, solve it on paper, take a clear picture and upload. So
All right,
anyway,
that sounds good.
if anybody that submit typed work, we actually fail the classwork. So anyway, I think you get the point. Let's go back. Any other question before we continue? Any other question? Okay, good. So let's try this one. It says a card is drawn from an ordinary deck of its 2 cards. Find these probabilities of getting a jack, of getting a 6 of clubs, of getting 6 or a 3. Let's try the first one. Of getting a jack. Probability of jack, getting a jack. So we can see how many jacks we have. See jack right here. Jack. So you have the 4 jacks, which means that the probability of getting a jack is 4 out of 32 cards. 4 out of 52. So you have 4 divided by 52. 0.077. Approximately 0.077. or I can call it 7.7%. Yeah. Part B says of getting a 6 of clubs. Probability of, I make this to be 18. 6 of clubs, 6 of clubs. So you can look at the club. How many club arts have 6 on them? Look at the club right here. Only one of them have number 6 on it. Which means that the probability of getting a 6 of clubs is 1 out of 52 cards. Which means 1 divided by 52 cards. Let's change this to 1. With 0.01, 0.019. 0.019. Okay. And part C says of getting a 6 or a 3. The probability of 6 or 3 equals the probability of 6 plus P of 3. So that for 6, the probability of getting a 6, when you go up a little bit, you feel you have 6. How many do we have? 6. 1, 2, 3, 4. And 3 is 1, 2, 3, 4. So that the probability of getting a 6 or 3 is 4 over 6. There are 4 6s. So 4 out of 52. Or 3. There are 4 3s. So 4 out of 52. Which give us 8. What about 52? 8 over 52 give us you can check it out here on a calculator. 8 divided by 52. 0.154. 0.154. 0.154. Or I can call it 15.4%. Any question on that? Yeah. All right. Excellent. Excellent. Now, the question might be asked in different forms. There are different ways that I ask this question. Okay. In 1 minute, let me take a quick look. Okay. All right. Okay, look at this one. See, a different way of asking these questions when 2 dice are involved. See, 2 dice are rolled. Find the probability of getting A, the sum of 7, B, the sum of 9, C, the same number of both dice, D, the sum of 11. Now, I show you how to get this chart. You can keep these charts. You can print it and keep it handy. But if you count them, there are 36 groups there. Now, with that in mind, we can now find the probabilities that we're looking for. Okay. First one is part A. Let me make this into be 18. Okay, that's better. So that A says find there are 2 dice are involved now. That's why you have two points inside each group. So A said the probability of getting the sum of 7. Probability of sum of 7 equals, well, how many of them add to 7? If you look at this place, 6, 1 give us 7. 5, 2 give us 7. 4, 3 give us 7. 3, 4 give us 7. 2, 5. So 1, 6. This all the sum of 7. So 6 plus. So how many of them? 1, 2, 3, 4, 5, 6. So you got to be 6 out of 36. Okay, 6 by 36. 6 divided by 36. Give me 0.167. 0.167. 0.167. Okay, that settles that. So part B says the sum of 9. B, probability of the sum of 9. Sum of 9 equal. How many? You check the one that give you 9, like 6, 3 give us 9. 5, 4 give us 9. 4, 5 give us 9. 3, 6 give us 9. That's if you add them, So how many of them? 1, 2, 3, 4. So you be 4 out of that 6. So I have yeah, 4 divided by 36. 0.111. 0.111. Part C says the same number on both dice. The same number on both dice. Well, probability of the same number on both dice. Same number on both dice. Okay. You look at the chart. So where we have the same number, say 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. 6. These are the ones that give us the same number. Both dice. So you have 1, 2, 3, 4, 5, 6. So that's 6 out of that 6. Which is 0.167. Since we did a calculation before on part A. Then part D say the sum of 11. The probability of sum of 11. Sum of 11 equal. Okay. So only two numbers, you see 6 and 5, and 5 and 6. Only these two give us 11. 6 plus 5 is 11. 5 plus 6 is 11. So only two of them. 2 out of 36. So we go to 2 out of 36. Okay. 2 divided by 36. 0.056. And approximately 0.056. Okay. 0.0556. Any question on this? Any query? Okay, excellent. Now, we might have it in different form, like this one, the slot. Roulette. So roulette wheel has 38 slots. 0, 0, 0, 1, 2, 3 to half. Say half of 1 through 36 are red, and the other half are colored black. The remaining numbers 0 and 0 are colored green. We find the probability that a ball lands on A black number, B, a green number, C, a 10, D, an odd number. So the first thing to do is to get the sample space. Let's use B for black, G for green, and R for red. Okay? So, which means that our, okay, B, roulette, you can see the roulette, this is how it looks like here. So you can see the half of, you see, half of 1, 0, half of 1, 236 are red. That means 18 are red. You can see 18 are red. Then another 18 are black. They have 2 that are green. You can see the green ones here. So that means B should be 1, 236, 18. That's black. And red, so R equals 18. Then the remaining number, just 0 and 0, 0 are colored green. So green, G equals green, 2 of them. Now you can put your, add them so you can get your total. So give us 18 plus 18 plus 2. 18 plus 18 is, let me see. We got 18 plus 18 plus 2 is 28. Sorry, I'm sorry, my mistake. 18. That is 38 slots. 38. 38. 38. That is your sample space. Now, with this, we can now answer the questions. The first question says, find the probability that a ball lands on a black number. So that we can have that the at A, the required probability that it lands on a black number. There are 18 black numbers. That means 18 divided by 38. I'll make this way. 18, size 18. See? 18 over 38. So 18 divided by 38. 0.474. 0.474. Okay? Got 0.474. Okay? Or you can call it 47.4% chance that it lands on a black slot or black number. B says to find the probability that it lands on a green number. Okay? On a green number. So that the probability of green of G equals, there are only 2 green numbers. So you gotta be 2 by 38. So we go to calculator, we can get that from calculator. Okay. Change this to 2. Give me 0.053 approximately. 0.053. That's 0.053. Okay. Part C says that it land on a 10. We look at this roulette. Only one number is 10 here. Let me see. See, there's only one 10. I can see right here. Only one 10. So probably the probability that it lands on 10 equals 1 out of 38. Okay. That 8 equals oh yeah, we gotta go to calculator. Switching to 1 to 38 is 0.026. 0.026. Okay, 0.026. Okay? 0.026. Okay. T There's a probability that it is land on an odd number. An odd number. Well, odd number, if you look at the roulettes, you say that half of them, see, half of 1 through 36 are red, and the other half are color black. We look at half odd that out of 38 numbers, half actually 36 will start from 1 to 36. Half of them will be odd. That means about 18 the odd number, and the other 18 will be even number. So we have the required probability that on the odd number, it be odd 18 out of 38, which gives us 0.474 approximately. So any question on this one? Any question? So no question. Excellent, excellent. Now we can look at some basic rules of probability. Okay. So I think we have already done that. I have introduced you to that already. They can take you down there so you can see more. So look at the basic rule. Rule number 1. The probability of event E is a number, either a fraction or a decimal or percent. I think I mentioned it already, between 0 and 1. That's why we write it in this form. In this form, we have 0 to 1. Then the second rule says, this will mean that the probability of an event can never be negative, can never have a negative value. So if you have your answer as negative, you have failed the equation. Or it can never be greater than 1. Rule number 2 says if an event cannot occur, then it has a probability of 0. I mentioned that already before. Rule number 3 says if event is certain to happen, then the probability is 1. Then the other one is complement rule. I'll take you back to complement rule. Complement actually means the event. Let me bring it down. The complement of an event is the opposite of that event. That's the simplest way of explaining it. It is the opposite of that event. So and we use this symbol E with a little c at the top to represent complement, or I can use E, or E represent the event. Okay. So if you look at these examples, say find the complement of each event. Say selecting a letter of the alphabet and getting a vowel. The complement is not selecting a letter that is not a vowel, like selecting B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X, Y, and Z. Sorry. So the complement is the opposite. You say selecting a letter that is a vowel, selecting a letter that is not a vowel. How about this? Selecting a month of the month and getting a month that begins with J. That means selecting months that doesn't begin with J. Okay, that means selecting February. We say selecting a month and getting a month that begins with J means selecting a month that does not begin with J. That's the complement, the opposite. Selecting February, March, April, May, August, September, October, November, and December. Okay? So complement is opposite. The complement of you sitting down is you standing up. The complement of you being here today in this class is you not being here. So it's basically the opposite. So now we use this. I already explained this. Now for each complement, there's an important rule. It says that the probability of E complement is equal to 1 minus the probability of E. And that the probability of E is 1 minus the probability of E complement. We use this important formula to finding probabilities when complements are involved, and also when we are doing at least probabilities. Let's look at this particular one. It says, in a lottery game, each player chooses a 3-digit number between 000 and 999. So a player wins if his or her 3-digit number is chosen. Find the probability that a player buying a single ticket loses the game. Now, when you buy a ticket, you want to win. But here, I ask you to find the probability that you lose, which is the complement of winning is losing. So obviously here we are looking for the complement. So the event win, this is for the numbers goes from 000 to 999. That means 1,000 slots there. 1,000 3-digit numbers. So let's use W for win. And we use W complement for lose. Now, a player wins if his 3-digit number is chosen. So he bought a single ticket. That means the chance of winning, Q of win, okay, will be equals 1 out of 1,000. Yeah? Because one ticket win or lose again. So 1 divided by 1,000. 0.001. Okay, 0.001. So that he wins. Okay? So that the probability that he loses, that means W complements, that he loses, okay, will be 1 minus the probability that he wins. Means 1 minus 0.001. And that will give us 0.999 or 99.9% chance that he loses. So that's how we use complement. We're still going to come back to this complement rule again as we proceed in this topic. Any question before we go into empirical probability? Okay, no question. Good, excellent. Now, let's look at empirical. For empirical probability, unlike the classical, we don't know the sample space size of it. So we have to estimate it by ourselves. That's why it's empirical. And for that, we use this formula. Under the empirical probability, we use this formula. The probability of event A is equals to the frequency of event A divided by the total frequency. I will start with one example, and then we can examine more concepts and do even more examples. Okay? Yeah, let's start with that first example. Okay. It says, hospital record indicated that the maternity patient stayed in the hospital for a number of days shown here. it says, like you can see the number of days. Like you can see the number of days and then frequency. It says, find these probabilities that the patient stayed exactly 5 days, that the patient stayed less than 6 days, that the patient stayed at most 3 days, at most 4 days, that the patient stays at least 5 days. So first thing is to get the sample space, which is total for this. So let me write them down so I can get the total. I got 15 plus 32 plus 56 plus 19 plus 5. So let's do it. I'm gonna calculate the total. Got 15 plus 32 plus 56 plus 19 plus 5. 127. 127. Okay. So now with that, we can now find the probability. Say a patient stayed exactly 5 days. So part A, we're looking for the probability that he stayed exactly 5 days. Okay. So you can see from the list, 5 days, see what this is the number of days they stayed. And answer is 56. But that's for exactly 5 days. It's 56 out of 127. So you have 56 out of 127. So you can go and get it from here. 56 divided by 127. 0.441 approximately. 0.441. Okay. 0.441. But there's 44.1% chance that the patient stayed at least 5 days. I mean, stayed exactly 5 days. Okay. And now the B part says the patient stayed less than 6 days. Okay. Part B, patient stayed, probability that they stayed less than 6 days. Equal. See, look at 6 days right here. So less than 6 days from 5, 4, and 3 are less than 6. So that the probability that they stay less than 6 days becomes probability of 3, P3, plus the probability of 4, plus the probability of 5. You cannot include 6 because it's less than 6 days. That will give us these answers. For 3 days, we have 15 divided by 127. 15 divided by 127. Plus, for 4 days, is 32 by 127. And for 5 days, we have 56 by 127. Okay. Which means, let me write this down so we can get the answer from the calculator. Got 15 for 127 plus 32. 127 plus 56. 127. So you got 15 divided by 127. Okay. Plus 32 divided by 127. Okay. Plus 56 divided by 127. Give me 0.811. Okay. Okay, let's see. Okay, we have what did he give? He gave us 0.811. Okay. 0.811, or there's 81.1% chance that this patient stay less than 6 days. Now, the other one will be part C. The patient stayed at most 4 days. At most 4 days means 4 days or more. Let me start from here. 4, 5, 6, 7. So that the probability of staying, oh, sorry, my mistake. 4 days, at most 4 days mean 4 days or less, not 4 days or more. That means 3 and 4. So it's gonna be 4 days will be probability of 3 plus the probability of 4. So 4 days or less, that's what it means. Will be equals to, for 3 days, you have 15 by 127. 15 divided by 127 plus, for 4 days we use 32 over 127. Okay, equals, write it down, 15 over 127 plus 32 127. So you have 15 over 127 15 divided by 127, yeah, plus 32 divided by 127, 0.37 approximately, 0.37 approximately, 0.37. Yeah. And last one, that section will be part D. Part D says patient stayed at least 5 days. At least 5 days means 5 days or more. That means 5, 6, 7. So the probability of at least 5 days, 5 days will be, because the probability of 5, okay, plus the probability of 6 plus probability of 7. Okay, which is, for 5, we have 56 over 127. The 6 divided by 127 plus, for 6, you have 19 over 127 and for 7, you have 5 over 127 So let me write this down so we can calculate it. It is 6 over 127 plus 19 127 plus 5 127. So you have 56 divided by 127 plus 19 127 plus 5 157. 0.6299. So approximately 0.63. 0.63. So you can see how we estimated it. We estimated the probabilities and then calculated it. That's how we do empirical. Any question on this? Any question? Okay. So since there's no question, we can just discuss a few more concepts. First one is mutual exclusiveness. Two events are mutually exclusive if they cannot occur at the same time. So the occurrence of one event prevents the other one from occurring. For example, you cannot be event of being a Democrat or being a Republican. You cannot be a Democrat and also be a Republican. It's not possible. Now, how about this? Getting a 4 and a 6 in one single card. Not possible. At the intersection on the main road, either you turn left or you turn right. You cannot turn left and right at the same time. And so on. So you get the picture. Now, dependent events. Two events are dependent if the outcome of event A affect the outcome of event B in such a way that the probability will change. For example, having a good grades if it's an event and getting a scholarship. So if you have good grades, you get a scholarship. That's dependent. No parking zone. Don't park there. You get a parking ticket. So if the event, no parking zone, an event parking in a no parking zone. So if you park in a no parking zone, you get a ticket, parking ticket. And so that's kind of events are dependent. Now there are independent events which occur when the two events are not the occurrence of event A does not in any way affect the occurrence of event B. For example, drawing a card from a deck. The deck has 52 cards. So if you draw a card, before you draw the card, there are 52 cards. Then if you put it back and take another one, when you put it back, you still get 52 cards. So the outcome cannot be changed. The probability cannot change because you put the card. But if you didn't put the card back, that means now you have 51 cards. That means the probability will change. How about this? Winning the event winning a Maryland lottery and the event winning a New York lottery. They are totally independent. That you win a Maryland lottery doesn't mean that you're going to win a New York lottery. Except you are so especially you are so one of the luckiest person in the world. Anyway, I think you get the point. For the first one, the first concept, which is mutual exclusiveness. This is the probability we use. Probability of A or B. We call it addition rule as a matter of fact. Addition rule. A or B is probability of A plus the probability of B minus the probability of A and B. Now, if the two events are mutually exclusive, this part will turn to 0. So that means you're going to have PA plus PB. For independent events, we use AND. We call it multiplication rules. The probability of event A and B equals to the probability of A times probability of B. And there are three events. Probability of event A and B and C. And is the keyword there, and. That's how you know you're going to use multiplication. For addition rule, or is the key. So you got it PA times PB times PC. And for when they are dependent, that means a little change. A and B becomes the probability that event A will occur times the probability that event B will occur, given that event A have already occurred. And of course, this / means given that. So if there are three events, P of A and B and C becomes P of A times P of B given A times P of C given AB. Let's see how this works. Okay. Let's see. So look at this question. I'm gonna move it. Okay, this place should be enough for it. It says here, at a political rally, there are 20 Republicans, 13 Democrats, and 6 independents. If a person is selected at random, find the probability that he or she is either a Democrat or an independent. The keyword there is or. That's how you know you're going to use addition rule. So let's see R for Republican, D for Democrat, and I for independence. We are looking for either a Democrat or an independent. Okay? So we look for the probability of Democrat, D, or independent, which will be P of Democrats plus P of independents minus P of Democrats and independents. So if it's a mutually exclusive event, this part will count to 0. So for Democrats, before you can do that, we need to get the how many the sample space. They said that event have 13 Democrats, and for the Republicans, we have 20. And for independents, we have 6, giving us a total of give me 1 minute. Let me put the line here. If you add them together, get the sample space. Write this down. Okay. As a matter of fact, I can do it off head. 6 plus 3 is 9. Let me see if I still remember my maths. 6 plus 3 is 9. And then 2 and 1. 1 plus 2, because this 6 goes on this side. Yeah. 9. This one, 1 plus 2 is 39. Okay. 39. Sample space is 39. Okay. 39. Okay, now we can now apply this. P of D or I equals P of D plus P of I minus P of D and I. So for this people, Democrat is 13 out of 39. Plus independent is 6 out of 39. Minus the probability of dependent and Democrat and independent. It can be Democrat and independent. So it's 0. That's 9. So let me write this down. 13 over 39 plus 6 over 39 or 0 over 39. Let's go and put this on the calculator. We have 13 divided by 39. Okay, plus 6 by 39 minus 0 by 39. Make sure I've seen this. Yep. 0.487 approximately. 0.487 approximately. 0.487, right? 0.487 approximately. 0.487. Or I can say 48.7 chance. So that it should be a Democrat or an independent. Any question on this? Yeah. Excellent, excellent. So let's look at another example. I'm gonna try this one. A card is drawn from an ordinary deck and then replaced. Then a second card is drawn. Find the probability of getting a queen and then an ace. And means you're gonna be multiplication rule, and is a keyword. A queen and an ace. For cards, we already know that a card in a deck, we have 52 cards in a deck. Let's use Q for queen and A for ace, so that the probability of getting a queen and an ace will be equals a queen and ace. You can see queen right here. And you can see an ace. They're not, it cannot be a queen. A card cannot be a queen and at the same time be an ace. So getting a queen and an ace will be for queen, it's going to be probability of queen times probability of ace, which will be equals queen. There are 4 queens. You can see the 4. 1, 2, 3, 4. There are 4 queens and there are 4 aces. So it's going to be 4 over 52 times 4 over 52. So let me put it in. Okay. We got 4 divided by 52 here times 4 divided by 52. 0.0059 approximately. 0.0059. Okay. 0.0059. So that's for to get a queen and an ace. Okay. Any question on this? Any query? Okay. No question. Good. Excellent. How about this one? A person has a collection of 30 CDs. 30 CDs, of which 5 are country music. If 2 CDs are selected at random, find the probability of getting or that both are country music. Now it didn't tell us whether it is replaced after the first. Like it said, a person owns a collection of 30 CDs, of which 5 are country music. If 2 CDs are selected at random, it didn't tell us, unlike this one that we just did. It said a card is dropped on a deck and then replaced. They didn't say that here. Say if 2 CDs are selected, so we assume that they were not replaced. Find the probability that both are country music. Let us use C for country music. So 2 CDs are selected out of 30 CDs. So let's say that we're looking for the probability. We're looking for the probability that the first CD, C1, is a country music, and the second CD, C2, is a country music. So that means that dependent event. If they didn't put it back, that means it will change the probability. When they made it, before you make this first selection, so there's 30 CDs, out of which 5 are country music. So there are 5 country music and 30 CDs before you make the first selection, and you select 5. So the chance of getting a country music will be 5 out of 30 times. Now you didn't replace it. So now we have 29 CDs and 4 country music. So that'll be 4 over 29. And that will give you the answer. So I'm going to write this down so you can get the answer from this. 5 over 30 times 4 over 29. Okay? Let's go and get it. 5 over 30. Okay? Times 4 over 29. 0.023 approximately. 0.023 approximately. 0.023. Okay? Or 2.3% chance that both are country music. Any question on this? Any query? Okay. Question. Okay, good. Let's try number 12. But 12, I can bring it up a little bit. It's a Harris poll. You know what? Let me bring it down so you can see it clearly. And move this one down. Okay. Oops, excuse me. Say Harris poll, make it R18. Okay, that's better. Harris poll found that 46% of Americans say that they suffer great stress at least once a week. If 3 people are selected at random, find the probability that all 3 will say that they suffer great stress at least once a week. So in this case, we have let's say that 40% of Americans. So that means S, which is stress, is 46%, which is 0.46. So there are 3 people selected, and you are asked to find the probability that all 3 suffer great stress. So you have for the probability that the first person, S1, suffer great stress, and the second person, S2, still that they suffer great stress, and the third person, S3, still that they suffer from great stress. Will be S1, probability of S1, excuse me, probability of S1, okay, times probability of S2, okay, times P of S3. S3, which is equals, we have it as 46. So you're going to be 0.46 times 0.46 times 0.46. Okay? 0.46 times 0.46 times 0.46. Let me get it from here. 0.46 times 0.46 0.097 approximately 0.097 0.97, or there's 9.7% chance that all 3 will say that it's for great stress. Okay. Any question on this one? Hello, scholars. Any question? Okay. No question. Good. Now let's look at this last example for tonight. It says the result of 985 pedestrian deaths that were caused by accidents are presented below. You can see the pedestrian intoxicated or the driver intoxicated. For the driver intoxicated, we have yes and no. Yes and no. For the pedestrian intoxicated, we have yes and no. And it says, if, gotta make this into the thing. Okay, it says, if one pedestrian death is randomly selected, find the probability that the pedestrian was intoxicated or the driver was intoxicated. B, if 2 pedestrian deaths are randomly selected with replacement, what is the probability that in both cases, both the driver and the pedestrian were not intoxicated? So the first thing is to find the totals for this table. For that, I'm going to get my pen and write this down. First of all, 59 plus 79. I got 59 plus 79. 138. 138. 138. Got 138 here. Then 260. Okay, I'm going to write this one down. 266 plus 581. So got 266 plus 581. 4847. We can put it right there. 847. Then have this one. This get the total for this one. 59 plus 266. 59 plus 266. 325. 325. Then 79 plus 581. 79 plus 581. 660. 660. Now let us check our work, make sure that our answer is correct. They should all add to 985. Let's try this side first. 325 plus 660. 325 plus 660. 325 plus 660. Okay, what are we missing? Oh, I wrote 328. 325. So give me 985. 985. 985. 985. As a check, let me add this one. 138. Yeah, 138 and 847. 138 plus 847, 985. So it corresponded. So we answer once this place, you've got to be careful. If you make any mistake on this table of values, all your answers will be wrong. So you got to be careful there. So anyway, now we use P to represent pedestrian intoxicated, and then complement. Let me make it bigger so you can see it. Make it 18. P for pedestrian intoxicated, P complement for pedestrian not intoxicated, D for driver intoxicated, D complement for driver not intoxicated. Now the first question says, if one pedestrian death is randomly selected, find the probability that the pedestrian was intoxicated or the driver was intoxicated. That keyword "or" here tells you that you're going to use addition rule. So that's what I use here. P, probability of P or D. So that means P of P plus P of D minus P of P and D. So equal. So we're gonna apply this. So pedestrian intoxicated P, that's the probability of P. That's P here. Intoxicated is yes, can see the yes right here. And total is 325 out of 985. 325 for 985. Plus now next one is P of D. That means the pedestrian driver intoxicated. But the question was, find the probability that the pedestrian was intoxicated or the driver was intoxicated. So yes for pedestrian and yes for driver. So we have for driver was intoxicated is PD. For driver, this is driver right here. Yes, it's 138 out of 985. Out of 985. The minus P and D intoxicated. That means pedestrian was intoxicated and the driver was intoxicated. See, you can see both of them right here. Yes And yes, you can see they intersect here. This is where both of them are intersected. 59 over 985. Yeah. So we can now finish it. We can now round it up. Okay. And this section here. So let me write this down. 325 over 985 plus 138 over 985. And that's 59 over 985. Let's put it in. So you have 325 divided by 985. Okay. Plus we got 138 divided by 985 minus 59 divided by 985. 0.410 approximately 0.410. 0.410. Okay. Any question on this? Okay. No question. So let's try the second one. Say if the two pedestrian desks are randomly selected with replacement, what is the probability that in both cases both the driver and the pedestrian was not intoxicated? This one is easy to find. The probability that's part B. The probability that both the driver and the pedestrian was not intoxicated. So P complement, and D complement. The pedestrian and the driver was not intoxicated. Let me grab this right here. This is a complement, so you gotta be at the top, like a square, kind of. The top. Well, this one you can find this one very easily from the table. See, not intoxicated is no. Pedestrian is this side, and driver is this side. So this presents where both the pedestrian and the driver was not intoxicated. That means here. See, no on both sides. 581 over 985. 581 over 985. But there are two of them, so you have to square it. So you're gonna be 581 over 985 times 581 over 985. So you get 581 over 985 times 581 over 985. It's 581, right? Yeah, 581. So let's put it in the calculator. So 581, 985. Yeah. So you got I'm just gonna square it because you know what it means. 581 over 985. But there are two of them, so just square it, that's all. 0.348 approximately 0.348. So 0.348. Any question on this? Okay, no question. Yeah. So about to end the class now, and I'm going to put the class for. Can you hear me, guys?
Yes.
Are you there? Hello? Can you hear me?
Yes, we can hear you.
Yeah, now next week, if the weather is permits, we're gonna meet in the campus in our classroom, not in no, yeah, not a remote. So next week class will not be a remote class, provided that the weather is good. Okay. If you have a question, you can ask me now before we end the class. Any question for me? Hello? Any
Wait, I just came back from the bathroom though. Did you post the question for the is that the question right there?
No, I'm gonna
For the
put it after we class over, I'm gonna put it there.
all right, I'm just making sure because I really don't want to miss this assignment.
Yeah, I just said next week, Monday, if the weather is good, we'll meet in the campus, not in the remote. So next week class will not be a remote class, provided that the weather is good. Okay?
All right.
All right, guys. So as soon as we leave, I'll end the class now. Any question before I end the class so I can put the class? Any question for me? Okay, no question. Good. So we see next week then. You guys have a good evening.